Hi, we're Ram Pump. I'm Allie.
I'm Matt.
And the purpose of the Ram Pump is to optimize the Aquaclara. The purpose of our team is to optimize the Aquaclara vertical Ram Pump for providing plant plumbing. And
So the first thing is just a nice little background of what a ramp pump is. It's just a nice little crude drawing, not really to scale at all. But basically we get the water that goes into the plant, it gets treated, and the water gets out, but also in line with the water coming out is our ramp pump, so we can push the treated water back up to the storage tanks and be able to use it for plumbing and help with the coagulants and stuff, because it's just clean water that can be used. And this is helpful because it takes away the burden off of some workers and stuff, because you don't have to carry it, as we use gravity, so this is definitely lower than this is, so someone will have to carry the water up. So we use a ramp pump with spring with no electricity, which is on par with the rest of the plant, to bring the water back up to the top.
so this is what the Ram Pump itself actually looks like. It's composed of these two check valves that are connected by this middle brass connector. And this top check valve also has another valve out of it, which is where the effluent of the pump goes. And the influent comes in right through the top and exits through here when it's not being pumped. And then on the inside is this rod, which has a plate at the top, and then these two stoppers which adjust different dimensions. And then a spring is put on this bottom part, which is the bottom of the spring is supported by the inside of this bottom check valve. So basically how the Ram Pump works is the plate is open and like the valve is open, and water is coming in through the valve, and that water force eventually gets high enough to close the plate, as in it becomes greater than the spring force keeping the plate open. And once that happens, there's a big spike in pressure, at which point water begins to exit through the effluent and is then pumped up instead of going through the valve. And as that's happening, the pressure is then decreasing until it gets to a point where it is no longer greater than the spring force and the plate can reopen.
So in the lab, we mimic a nice little mimic of what a plant could look like. We have a nice head tank, which would serve as the gravitational potential that you would see in a plant. It's connected. We have the drive pipe down to where we connect the ramp pump to the bottom, so the water can drop and use just gravity and the spring that's in there to operate. On this side, we have the two collection buckets connected, so we have a sump pump so that we can push the water back up, so we can continue to test and have water moving throughout the whole plant as if water was continuously coming in. And then on this side, we have an air chamber, which allows us to use the ideal gas cell to see the efficiency of the pump, how high it's actually going, and then we can connect pressure sensors and stuff around the actual inside of the plate via this to try to model the behavior of what's going on inside.
So the last semester, the team worked a lot on mathematical modeling and making these graphs for the ideal velocity of the water in the drive pipe. And basically the main point of this is to show that the longer the plate is closed, the more efficient the pump will be, because the red curve is the velocity of the water when the plate is open, and then this blue curve is the velocity when the plate is closed, and then the area under the blue curve is the volume of water pumped. So this bottom graph shows that if this blue curve could have a shallower slope, and increase the time that the plate is closed, then you will pump more water.
So originally in the beginning of the semester, we decided we wanted to try to find a range of K values that we could always just be able to plug in numbers specific to each plant or each situation and be able to spit out what's the ideal lengths or values from like a minimum and maximum perspective. We soon realized that there's a lot of initial compression that has to do with, and there's a lot more than just the K values that really optimize efficiency by the spring. So we sought to find a new explanation for why our min and max values didn't always necessarily line up when we ran tests in the lab. We came to the main conclusion that they're only part of the equation. So we moved past that.
So going on from that, our new approach was to look at the K value really as what it is, which is a change in force over a change in distance. So the change in distance is easier to get because that's just the amount that the plate moves, which can be measured. And then for the change in force, we want the change in force to be the difference between the force that we want the plate to close at and the force that we want the plate to open at. And then this gives us what we believe is our most efficient K value, where as of now, we believe that the force when the plate is opening is the hydrostatic force from just the water column above the plate once the velocity is gone to zero, and the closing force is the maximum force that the moving water reaches when it gets to its final velocity. So we began to try to solve for those two forces. We began with the force from the water, the moving water, and we constructed a few experiments to try to find that.
The first thing that we did was we decided that we were dealing with the initial compression, which would be below the stopper for the spring, and we realized that if we changed that, we could effectively change the force of the spring. So we thought that we set out to explore changing that distance by moving the stopper down and seeing if at what point the plate could no longer close. So basically, at what force from the spring was it too strong so that the water never reached that force, and we thought that we could then infer where the water got to its max force. But unfortunately, we're dealing with very small distances here. Like, we are trying to increase this by like micrometers due to the fact that the plate only really closes like 1.3 centimeters total. And so it became that human error of moving this and tightening, because you have to tighten the stopper as well as the bolt here. It was just too hard to get an exact value. We could run the experiment 4 or 5 times and get vastly different values. So next we decided we rigged up the experimental the lab setup for another experiment. We added some supports to add 2 pulleys so that we could run string from the actual ram pump down here, which is shown over here, up over to a counterweight so that we could more efficiently judge the opposing force on the actual plate. And our first thing was, okay, we'll just put it on a scale and then we'll run it through and we'll see how much the weight of the counterweight on the scale changes. The main problem with this, though, is that we realized that you really need to have the plate be disengaged from the check valve to get accurate readings, or else the change in weight is also giving you the change in tension force from the check valve. And it became, and then once again, because it's only like a total of 1.3 centimeters, it became very difficult to be able to start with the plate just barely disengaged. And then we weren't getting any accurate readings. We were getting way lower forces than seemed even possible.
So finally, we tried another experiment that actually worked. And so we used the same pulley system, but instead of having the bottle on, or the weight on a scale, we just had it suspended in air. And we used this water bottle full of water as our weight. And then what we did was we ran the pump and made sure that the amount of water we had in the bottle would keep the plate open. And we emptied the bottle little by little until that was no longer the case, until the plate would close from the force of the water. And then we did add in very small increments water little by little again until the plate would stay open again, and then we used that weight of the bottle to find the force from the water, because the force from the water would be the weight of the bottle minus the weight of the rod in water, since the tension is also supporting the weight of the rod. And this gave us a result of 7.423 newtons for the force from the water moving at the final velocity of our system. So in the future, the team can look at the other aspect of our most efficient K value equation, which would be the force at which the plate opens. As of now, we suspect that this is the hydrostatic force. However, we would love for that to be confirmed by pressure sensor data, or maybe other experiments. So that is something to do in the future, and if it is not hydrostatic, figure out what it is. And then from there, so as it was shown earlier in the ideal velocity graph, the velocity of the water in the drive pipe has an asymptote. So it is believed that actually having the plate close before it reaches max velocity might increase efficiency so that you don't have to wait to get to that point. But nothing has ever been done to find where that cutoff is. So a way to do that would be to first find the force from the water with the outlet of the pump at different heights, so that you are essentially finding the force from different velocities, and then using those forces in that ideal K value equation to find the different K values for the different cutoff velocities, and then ordering springs based on that and running efficiency tests with each one to find the most efficient cutoff one. And yeah, we think that that's a good direction to head in. So our contact information, and we do have a few appendix slides, which just detail the calculations from and results from our experiment, and the conditions that we believe lead to max efficiency and why, and fabrication details on how we connected this hook to the plate for our experiment.